Welcome to this second part of the DFT course. So last week was the first part on the basic theory. And this week we will focus on the approximations used in practice. So I remind you that you can have a look at the lecture notes at this address. And also at this review article, the link is in the chat window. Which is particularly relevant for the approximations because I have described many approximations in details in this review article. Okay, but before we really start, let me recap briefly what we have seen last week. So we have defined the universal density functional f of rho as the minimum of a multi-determinant wave function giving a fixed density rho of the expectation value of t plus WEE. And the minimizing wave function is called psi of rho. But next, to have an actual scheme that we can use, we use the Conjunct scheme, where we decompose this universal functional into TS, EX, EH, and EXE. So TS is a non-interacting kinetic energy functional, where you minimize the expectation value of T over a single determinant wave functions, giving a density rho. And the minimizing Slater determinant is phi of rho, okay, is the Conjunct determinant. The R3 functional is defined as this. And the exchange correlation functional, the quantity that we need to approximate in practice, can be decomposed into an exchange part, which is defined with the Conjunct determinant as this, and the correlation part, okay, which is all the rest. And you can check that it is this expression. And an important thing to realize here that we will use is that it contains two contributions. So the one coming from the kinetic energy, T contributions. So that's the correlation kinetic energy contribution, TC. And then the rest, the WEE, gives a potential correlation contribution that is called UC of rho. And so finally, in the Conjunct scheme, we can write the exact ground state energy as the minimum over a single determinant of this expression, where you evaluate your functional at the density of your Slater determinant phi. And okay, and so in this course, we will in particular we will see approximation for the exchange and correlation functional, and so we will see, of course, the first approximation, which is the local density approximation, but also the so-called generalized gradient approximations, where you introduce the gradient of the density. Next, there is also another scheme that is used in practice called the Generalized Conjunct scheme, and which is similar to Conjunct. So you minimize again with respect to Slater determinants, but now you have an exchange correlation functional of the single determinant phi, and not simply of the density. And this functional can be defined as almost any functional S of phi plus a complementary functional depending on the density of phi. So you have a lot of freedom in defining this exchange correlation functional here. And this is usually in this generalized Conjunct scheme that are understood the approximations, the other type of approximations. So they are the meta-GGA approximations. So I will explain that. And also the hybrid approximation, where you have a fraction of artifact exchange. And towards the end of the lecture, if we have enough time, I will also introduce another extension of the Conjunct scheme, the so-called multi-determinant extension of the Conjunct scheme, which allows you to define other families of approximations like the double hybrids approximations. Okay, so now we will continue the course. And before we really go into the actual approximations, and correlation energy density, because that is usually the quantity that is approximated in practice. So exchange and correlation energy densities. Okay. And first, I need to define the so-called exchange and correlation holes. Okay, so we can define what is called the pair density associated to the wave function that was called psi of rho, the one that minimizing in the expression of the universal density functional. And the pair density corresponding to this wave function is defined as rho 2 of R1, R2, and n minus 1, that's just the normalization constant. And then you integrate the square of this wave function. So it depends on spin and space coordinates, x1, x2, xn. And you integrate over the spin coordinate of the first electron, the spin coordinate of the second electron, and then all the coordinate of the third electron until the last one. And this is proportional to the probability density of finding two electrons at position R1 and R2, and the rest and the remaining electrons can be found anywhere. So why this quantity is so useful is because this is all what you need to define the expectation value of the Coulombic electron-electron interaction over this wave function. Okay, you can show that this expectation value is just 1/2, and then the integral of this pair density integrated with the Coulomb interaction. Okay, integrated over R6. So that's useful. Now, what we can do with this quantity is to define a sort of R3 and exchange correlation contributions. So rho 2 can be decomposed into the product of the density at R1 and the density at R2. That's sort of the R3 contribution to the pair density. And then all the rest is called rho 2 XC. That is the exchange and correlation contribution to the pair density. And this exchange and correlation contribution to the pair density can itself be written as the product of the density at R1 times a quantity that is called HXC of R1 and R2. And this is the exchange and correlation holes. Okay, and you can consider it as a modification of the conditional probability of finding one electron at R2, given that one has been found at R1. That's a modification due to the exchange and correlation effects. So there is one important property of this Hall. It's that you can show that it integrates to -1 if you integrate it over R2. Okay, so it contains one negative charge, if you want. Okay, so now let's define exchange and correlation contributions to this quantity. Okay, so for this, we first define the Conjunct pair density. That is, this is the density that the pair density that we define with the Conjunct single determinant wave function phi of rho. And this pair density, I will call it rho2 Conjunct. Okay, so that's the same definition as before, but you replace psi by phi. And again, I can decompose this Conjunct pair density into an R3 contribution composed by the product of the densities, and then a purely exchange contribution, because there is no correlation in Conjunct, in the Conjunct pair density. So exchange R1, R2. Okay, and again, you can do the same definition. So you can write this as the density at R1 times the exchange Hall, R1, R2. Okay, so that's the definition of the exchange Hall. And it has some properties. There is a sum rule for this exchange Hall. So if you integrate it over R2, it gives -1 as the exchange and correlation one. And there is an additional property that you can show coming from the fact that it comes from a single determinant. You can show that this Hall is always negative. And so if you plot this Hall, well, it typically in a lot of systems, it will look like that. So if I plot, so if I put the coordinate of the first electron here, R1, and if I plot with respect to R2, this exchange Hall, well, it will look like that. So it's always negative. Okay, and so it represents a decrease of the conditional probability of finding the second electron close to the first one here due to exchange effect. Okay, so this quantity is of course important in order to have an expression for the exchange energy functional. Okay, so the exchange functional, you recall that the definition is the expectation value of the Coulombic interaction over the Conjunct determinant minus the R3 functional. And so if you plug the definition of the pair density in this expression, you can find quite easily that the exchange functional can be written as 1/2 integral over rho of R1 times the exchange Hall at R1, R2, and you integrate with the Coulomb interaction over R1 and R2. Okay, integrate in R6. So that gives you sort of a convenient expression for the exchange energy, and you can define what is called the exchange energy density as follows. So this you write it as the small ex, which is a functional of the density, but also a function of, let's say, R1, and you integrate over R1. Okay, and this quantity is defined, of course, by the integration of this over R2. So this is called the exchange energy density. And sometimes we also define what is known as the energy per particle. I will write it here, which is simply that you take out a factor of the density in front. So you have the density at rho 1, and then the exchange energy per particle, we call it epsilon x, which is also a complicated functional of the density, and a function at R1. So that's the exchange energy per particle, and depending of cases, it is easier to think in terms of the energy density or in terms of the energy per particle. Okay, so that's the actual quantity that we will approximate in practice. Now let's define now the correlation Hall. Of course, it is defined simply as the difference. So the correlation Hall at R1, R2 is the exchange correlation Hall minus the exchange Hall. Okay. And since these two quantities are normalized to -1, if you integrate over R2, then it means that the correlation Hall integrates to 0. Okay, which is an important property. It is not necessarily negative. In fact, since it integrates to 0, you must have negative and positive parts of the correlation Hall. So a typical shape for this correlation Hall is as follows. So let's plot HC R1, R2 with respect to R2. Again, I put the reference for the first electron at R1 here. And then a typical shape is something like that. So it has positive and negative parts here. Close to the first electron, it is negative because you always have a decrease of the probability of finding the second electron close to the first one due to correlation effects. And here you notice that I've plotted something sharp, okay? And this is what is called the electron cusp condition. Because of the singularity of the Coulombic interaction, where two electrons are on top of each other, you have a derivative discontinuity here, like the absolute value function. So this is something that you didn't have in the exchange Hall. Here it was completely smooth, but now you have a derivative discontinuity. Okay, so what can we do with this correlation Hall? Well, in the same way that the exchange Hall was useful to express the expectation value of the Coulombic interaction, here you can also do that for the correlation part. But now what you can express is not the entire correlation energy, but simply the potential contribution in the correlation energy. So something that I've called, you remember, UC of rho.
Julien?
Yes.
Excuse me, because somebody wrote a question. I guess with your plot of the whole, you answered it, but can you have a look? Can you see the question?
Yes. Okay. Thank you. I didn't see. So what is the physical meaning of the exchange correlation Hall? is it something like a region in space around an electron 1 that an electron 2 is prohibited to be? And another doubt. Okay, so for the first part of the question, so this is, well, it is a decrease of the conditional probability of finding electron 2 given the fact that electron 1 has been found at position R1. Okay, so due to exchange and correlation effects, so you decrease basically the probability that electron 2 is close to electron 1, but you cannot say that electron 2 is prohibited to be in a region of space. You still have in general non-zero probability for electron 2 to be close to electron 1. So that's for the first part of the question. And the last part, what is the meaning of the -1 as a result of the exchange hole? Well, the meaning, so it's always difficult to answer this kind of question. What is the meaning of something? So, but you can interpret that as saying that the exchange hole contains one negative charge. Okay, that's one way of viewing it. And but if the question is how do you find that? Well, you have actually in the lecture notes an exercise with a solution where this is demonstrated. So you can do this exercise and you will see it's not too hard to demonstrate. So I don't know if that answers your question. Yes. Okay, so let's continue. So the UC of rho, the potential energy contribution, is, as you recall, psi of rho, WEE, psi of rho, and then minus the expectation value over the Conjunct determinant. Okay, and if you plug in the definition of the pair density and the correlation part, you will realize that this can be written as 1/2 integral of rho of R1 times the correlation rho, R1, R2, times the Coulombic interaction. And you integrate in R6. But this is not the entire correlation energy. Okay, that's only one part. We miss the kinetic correlation part. So in order to sort of include the kinetic energy contribution to an expression like that, we need another tool, which is called the Adiabatic Connection. And this is what we are going to see now. Okay, which is quite a useful concept in DFT to obtain an expression for the correlation functional. Okay, so okay, so the way I will explain that is that we can generalize the universal density functional by introducing a coupling parameter in front of the Coulombic interaction. So I have a lambda, which is a parameter in R, let's say. And now I define a universal density functional depending on this parameter lambda. Okay. And how I do that? Well, I minimize over a multi-determinant wave function. But now in the expression, I have t plus lambda times WEE. Okay, so that's why I call it a coupling constant, because it is in front of the interaction. And the minimizing wave function in this expression, I will call it psi lambda of rho. Okay, so now this lambda, you can vary it. If it is 0, you have f of 0, f of lambda of 0, and you will completely remove the interaction part, so it will remain only the kinetic energy part. And if you assume that the Concham system is non-degenerate in its ground state, then you can, in this case, if you have only t, you can limit the wave function to be a single Slater determinant. And in this case, you will recover the definition of Ts, that is the non-interacting kinetic energy. Okay. Now, what is the opposite limit is when you take lambda equals 1, then of course you recover the usual f of rho. Okay. So in fact, this lambda defines an adiabatic connection between these two limits. It goes from the Concham system, basically, to the true system. So now if you take f of lambda, you can do the same trick as in Concham. You can decompose it into different contributions. So you can decompose it into Ts, which does not depend on lambda. But then you also have the R3 functional depending on lambda now, and the exchange functional depending on lambda, and the correlation functional depending on lambda, okay, because it depends on the interaction. And the R3 and exchange functional, it's easy to find the dependence on lambda because they are simply linear with respect to the interaction. And since lambda is just in front of the interaction, it means that this lambda dependent R3 functional is simply lambda times the usual R3 functional that I have defined before. Okay, and that's the same for the exchange. So we have lambda times the usual exchange functional. Now the correlation part is more complicated because correlation is a non-linear function of the interaction. So we don't know exactly the dependence with respect to lambda. But we can write, as we did before, that this lambda-dependent correlation functional is, the expectation value of t plus lambda WEE over this lambda-dependent wave function, giving the density rho, minus the same expectation value, but over the Concham determinant. Okay. Now, the trick to get rid of the kinetic energy operator and to express the correlation energy simply as a potential energy contribution, if you wish, is to take a derivative now with respect to lambda of this expression. So let's compute that. Let's take the derivative with respect to lambda of this correlation energy. Okay. And we are going to use the Hellman-Feynman theorem, which states that the contribution to the derivative coming from the derivative of psi of lambda in this expression is 0. Why is it 0? Well, this is simple to see. This is because this expression is variational with respect to variations of the wave function. Okay, it is defined as the minimum over any psi giving you the density rho. So if you vary psi by taking the derivative with respect to lambda, you don't change the density by doing so. So you are in this space. And since psi lambda of rho is the one at the minimum of this expression, it means that the derivative with respect to psi will be 0. So the only derivative that will remain is the derivative the explicit derivative with respect to lambda, which is here in the operator. So it means I'm going to find psi lambda of rho WEE. Okay, that's because the derivative of t is of course 0, and the derivative of lambda WE is just WEE, psi lambda of rho. Okay, and here, well, here that's easy because phi does not depend on lambda, so we have simply phi of rho WEE phi of rho. Okay, and now I don't have the kinetic energy operator anymore. And to obtain the correlation energy, now I just need to reintegrate with respect to lambda. So let's do that. So now I will add. Well, now let's do it like that. So now I integrate over lambda from 0 to 1. Okay, so this is, of course, if I integrate directly this derivative, I find the correlation energy at lambda equals 1 minus the correlation energy at lambda equals 0. At lambda equals 1, well, this is just the normal correlation energy. And at lambda equals 0, this is 0, because at lambda equals 0, there is no interaction, so there is no correlation energy. Okay, now on the right-hand side, if I do this integral over lambda, I obtain, well, just this integral from 0 to 1 of this quantity. Okay, and so therefore I have obtained what is known as the adiabatic connection formula for the correlation energy. The correlation energy is given by this expression, which is a very useful one. Now, since we don't have anymore the kinetic energy contribution, well, it is included in some way, but it is included through this integral over lambda. We can write this expression only with the correlation Hall associated to the wave function psi lambda. So we are going to get that the correlation energy is 1/2 integral over lambda from 0 to 1. And then I have the density at R1, the correlation Hall associated to this psi lambda. So I will call it HC lambda of R1, R2, and integrated with the Coulomb interaction. R1, R2, you integrate in R6. Okay. And you can notice that the only thing that depends on lambda in this expression is the correlation Hall. So in fact, you can define what is called the coupling constant integrated correlation Hall, HC bar, okay, which is the integral of HC lambda over lambda from 0 to 1. And you can express this as simply the integral of rho R1 HC bar R1 R2. In R6. And so again, you find a useful expression for the energy density of the correlation functional. So again, you can write this as an integral over R3 of quantity that you call small ec, which is a functional of rho, because the correlational is a complicated functional of rho at R1. Okay. Or again, you can also write this if you prefer as energy per particle. So that will be rho R1 epsilon C, which is a functional of rho and a function of our R1. Okay, and this is these quantities, either small ec or epsilon c, which is approximated in practice. Okay, so that was preparation for now introducing the approximations. So if you have questions about this, you can ask now. Okay, so we can then introduce the first family of approximations, which are called the semilocal approximations. Okay, so these semilocal approximations, well, the first approximation in this family is the local density approximation. So LDA. So that's really the first approximation that was considered really at the origin of DFT, and is still a very relevant approximation. So the idea is
Yeah, I'm sorry again.
yes.
Excuse me. So there is a question in the chat box about
Yes.
yes, sorry. Yeah.
So where the pair density is introduced because the locality of the exchange potential in the Conjunct scheme were insufficient. No, it doesn't have to do with the exchange potential. It's simply that we prefer to have approximation in terms of local quantities. And so, for example, here we want, let's say, an approximation for this quantity. And we want an expression for this quantity. Well, this expression is given exactly by this, integrated over R2. So that was just to find a formal expression for the quantity that we want to approximate. And sometimes some people want to approximate directly the potential, okay? But very often we also need a total energy, and so in this case you cannot simply approximate the potential, you also need the energy functional. Is that okay? Okay, so the local density approximation is rather simple. The idea is to write the exchange correlation functional in LDA as follows. So you, well, in the same form as we put it here, but now we are going to have the density. I will simply put R instead of R1, rho of R, and then I have the exchange correlation energy per particle of the uniform electron gas, which is not a functional of the density, but simply a function of the density at R. So a function of rho of R integrated over R. Okay, so this is the exchange correlation energy per particle of the uniform electron gas, okay, UEG, of density rho. Okay, so what is the uniform electron gas? Well, it's a model system that you can make in the following way. So you take a box of volume, let's say V, and you throw in some electrons, let's say capital N electrons. Okay, and you want a uniform density in space. So to obtain that, you are going to take an Hamiltonian, which is T plus WEE as usual, but then the external potential, you take it simply as a constant. Because if it is not a constant, then you won't have a uniform system. So it's just a constant to ensure neutrality. And then you consider the thermodynamic limit. So you consider the number of electrons going to infinity and the volume of the box going to infinity, so that the density, defined as the number of electrons divided by the volume, remains a constant. Okay, so that's your system. Now, it is not one system. In fact, it is a family of systems for any density that you choose. Okay, the density here is an external parameter. You fix the density that you want, can be any constant, and there is a uniform electron gas which has exactly this density. Okay, so in the LDA, what you do is that you consider that in your real system, which doesn't have a uniform density, now the density depends on R, you consider that at each point of space, R, you compute the density of your real system, which is rho of R. And instead of using the true energy per particle of your real system, you take, as a simple approximation, the exchange and correlation energy per particle of the uniform electron gas having the same density at this point. Okay. So that's a simple approximation, but it turns out that it is a rather good one. I mean, at least it is better than one could have expected. So now, what is the form exactly of this exchange correlation energy of the uniform electron gas? Well, for the exchange part, it is known exactly. It is a constant that we know, Cx. It is given in the notes. And then the density at the power 1/3. And this was already determined by Dirac very long time ago, and it is also associated with the name of Slater. For correlation, things are more complicated because we cannot, even though the system, the model system here of the uniform electron gas seems simple, it is not simple enough to obtain the exact analytical form for the correlation energy. So what we do is that we do some analysis. We know some high and low density expansions of this correlation energy, which I'm going to give you now. So in the low density, in the high density expansion, we know, okay, so instead of using the density, we often use the so-called Wigner size radius. Which is defined as the radius of the sphere containing, on average, 1 electron. So in other words, the volume of the sphere, RS3, so the Wigner size radius is RS. So this volume times rho must be equals to 1. Okay, that's the definition of this RS. And so you see it is inversely proportional to rho. So so when RS goes to 0, this is the high density limit. We know the exact expansion of this correlation energy. It is there is a constant with a diverging term in log of RS. And then there is another constant B plus another constant C times RS ln of RS, and then a higher other terms in RS. Okay. So this limit is also called the weak correlation limit. Even though the correlation energy goes to minus infinity in this limit, you may be surprised to learn that it is weak. This is because it is still weak compared to the exchange. Because the exchange, if you express it in terms of the same Wigner size radius, this is proportional to 1 over Rs. So the exchange energy diverges even faster in this limit than the correlation energy. And in fact, the kinetic energy is in 1 over Rs squared, and so it diverges even faster. So both exchange and correlation are weak compared to the kinetic energy. Now, the opposite limit that we also know about is the low density limit. That is when Rs goes to infinity. So low density limit. And then we have an expansion like constant divided by Rs plus B divided by Rs to the power 3 over 2 plus C Rs squared, etc. Okay. And this is also called the strong interaction limit. So even though in this limit you see that the correlation energy goes to 0, it goes to 0 at the same rate as the exchange energy. So the correlation becomes as strong as the exchange. And in fact, they become stronger than the kinetic contribution because the kinetic goes to 0 as 1 over Rs squared. So it goes faster to 0. So this is the strong correlation limit. And in fact, the correlation effects are so strong in this limit that the electrons crystallize on a Wigner crystal. Okay, they are on the lattice. And you have to consider this crystal in order to find these coefficients. Anyway, so we know these expansions, and in between we can do numerical calculations. We can do, for example, quantum Monte Carlo calculation. And at the end, the results are fitted to functions that fulfill these expansions. And there are two main parameterizations for the correlation energy in LDA. There is the so-called VWN, Vosko, Wilk, and Nusser from the 80s. And there is a more recent one due to Perdue and Wang in 92 that are used also. So you can find in particular in the review article the exact form of this PW92 parameterization for the correlation LDA functional. I should also say that I've focused on the non-spin dependent case, but in fact you can also consider the spin dependent case, and in this case you will have a correlation uniform electron gas energy, which will depend on both rho up and rho down, okay? And this is sometimes known as local spin density approximation, okay? But in this lecture, I will only consider the spin independent case for simplicity. Now, so the LDA is not as bad as one may have thought at the beginning. Still, for molecular systems, it is not very accurate. And in particular, it suffers from self-interaction errors. So you remember the self-interaction issue that I mentioned last week. Okay, so self-interaction error. It means that, for example, in for one electron densities, the exchange energy must compensate exactly the R3 energy. And the correlation must be 0. Also, for two electron density in a single Concham orbitals with different spin, you must have that the exchange is -1/2 times the R3 energy. Okay, these are exact conditions, and in LDA, it is not verified. So if you put here the LDA approximation, it won't be -EH. If you put here the LDA, it won't be 0. If you put here the LDA, it won't be -1/2 EH. And that's why, of course, the R3 functional is a non-local functional depending on rho of R1 and rho of R2. And in the construction of the LDA, you see it's a local functional. It depends simply of a single R. So it's very difficult with such a form to obtain these equalities here. Okay. So of course, this is not only relevant for 1 and 2 electron systems, which are not really important, but more generally, you encounter this issue for many electron systems. Okay. For this reason and for other reasons, then we need to go beyond the local density approximation. And this is the next step is the generalized gradient approximation. Maybe I should ask here if you have questions about the LDA before we go to the gradient approximations. No. Okay. So so let's talk about the second semi-local approximation, the GGAs. Well, generalized gradient approximations. Voilà. Alors, okay, so before, okay, and in fact, the next logical step after the LDA is what is called the gradient expansion approximation. Or GEA. Okay, so let me explain briefly this. So the idea is to do a systematic expansion in terms of the gradient of the density. So you can see that as a sort of a semi-classical expansion starting from the local density approximation. So you can write the exchange correlation energy functional in the GEA as the LDA, which is the first term, which is exact if the density is constant. But if it is not constant, then you have other terms. And the next term will be in the following form. So you will have a function that I'll call CXC, depending on the density. And then you have the density to the power 3/4. And then a term which is the gradient of the density divided by rho 3/4/3 squared, dr. And this is the, okay, you can continue this expansion. This is a second order expansion in terms of the gradient. This exchange and correlation coefficients can be divided into an exchange coefficient that does not depend on rho, and then a correlation coefficient which slowly depends on rho. Okay, And we know these coefficients, or at least we know estimations for the correlation part. And why we write it like this is because this quantity, so gradient of rho over rho 3 to the 4 to the 3 is called the reduced density gradient. And it is a dimensionless quantity. So it is nice to introduce this quantity. And it measures, of course, the inhomogeneity of the density in your real system. Okay. So since we are able to compute these coefficients, it seems that it is a very nice way to go beyond the local density approximation. And that was a hope at some point that we could construct systematically a correction to the LDA in this way. The problem is that in this, if you truncate this expansion, you sort of assume that this reduced density gradient is small. But in fact, if you take an atom or a molecular systems, it turns out that you can find regions of space where this reduced density gradient is very, very large. In fact, you can show that it diverges in the exponential tail of the density. And for this reason, this truncated gradient expansion is in fact very, very bad. Okay, so that's why it is not used at all. But it is used in another way in the generalized gradient approximation. We build some information from this in the generalized gradient approximation. So the GGAs really started in the 1980s, and it is based on a generalized ansatz compared to the GEA, which is as follow. Sorry, I'm looking for. Okay, so we can write GGAs as follows. So it will be an integral over, let's say, energy density in GGA that is written as a function of rho of r, like in the LDA, but now you add also the gradient of the density. But that can be any function here. It is not simply an expansion. But the difference with the LDA is that now you can have many possible functions here. There is no unique definition of the GGA. In fact, many GGAs have been proposed. Okay. So this belongs to the so-called semi-local approximation because the gradient of the density introduces, in some sense, semi-local information. Okay, with respect to the density at point R. It is usually a big improvement over the LDA for molecular systems. Okay, so some examples of GGA functionals that have been proposed. Some of the most used ones. There is, of course, the Gga 88, which is called B88 or sometimes simply B. And this is an exchange GGA functional. Okay. So you can find the formula in the review paper. It is a relatively simple expression, which has been chosen by Gga. So the B is for Gga. In order to satisfy some exact constraints. And it contains one empirical parameter, which is fitted to Hartree-Fock exchange energies of rare gas atoms. Okay, and it is quite used, and it now it is often combined with a correlation functional known as LEAP, correlation functional. So LEAP is for Lee, Yang, and Parr, and it has also been proposed in 1988. You can also find the formula in the review paper. It's more complicated, but basically it is one of the rare functional that is not constructed based on the local density approximation. Rather, it is constructed by starting from the so-called Collet-Salvetti correlation energy expression, which is an expression to estimate the correlation energy based on the Hartree-Fock pair density. And in fact, the second order derivative of the Hartree-Fock pair density. And what Lee, Yang, and Parr did was to turn this expression into a pure density functional by doing a gradient expansion of the Hartree-Fock pair density. And they obtained this correlation functional. It contains 4 parameters fitted to the helium atom. Okay. So now the next functional that I want to talk about is the Perdue-Wang 91 exchange and correlation functional. Okay, so this is a nice functional in the construction because it is quite systematic. So let me explain briefly this. So the idea is to really approximate the exchange energy per particle, epsilon x, at R1, let's say. So you remember the expression. It can be written as 1/2 integral of the exchange hole at R1, R2, integrated with the interaction, integrated over R2. Okay. And also for the correlation energy per particle, you have a similar expression. So 1/2 integration of the Kaplik constant integrated correlation hole, R1, R2, interaction integrated over R2. Okay, so you have this expression. Now, what you can have is if you start from the second order generalized, a gradient expansion approximation. So using this expression, you can derive the corresponding exchange and correlation holes. And so you can find the GEA here, in terms of the corresponding GEA holes. Okay, and you can understand what is the problem with the gradient expansion approximation in terms of holes is that because the holes that you obtain at this level of approximation does not fulfill the sum rule that I gave you and the negativity condition for the exchange part. So that is if you plot now the exchange GEA hole in terms of R2. Okay, so the first electron is here at R1. It looks like that. So at short range, it is reasonable. But then you have something that oscillates at long range, and also it can be positive. So that's very unphysical. Okay, because the exchange cannot be positive. So what Perdue and Wang did was, in fact, to introduce some cutoff in order to restore the condition So in order to restore the negativity condition, okay, so they wanted to restore this condition. So they cut all the positive part of the whole, like that. And in order to restore the sum rule condition, that is that the integral over R2 must be equal to -1, they introduced a cutoff so that, for example, here at this cutoff, the sum rule is satisfied and then all the rest is cut. Okay, so of course, sorry, here also this part is, which is positive, is removed. So of course, now you have something that looks a bit weird, but you have to do this integral over R2, and that will average out these discontinuities. Okay, and if you do that, you find that numerically an exchange energy per particle that is much more reasonable than the starting GEA expression. You can do the same for the correlation part. So for the correlation parts, if you plot the correlation GEA whole, you will see that it is also quite unphysical because again, you have this oscillation at very long range. So here we don't have the negativity condition, but we still have the condition that the correlation hole must integrate. Well, this is the coupling constant integrated one, which also integrates to 0. So in order to restore this condition, again, they introduced a cutoff. For example, here, so that this is satisfied. Okay. And if you do that, you obtain, and then you do the integration in this expression, you obtain a correlation energy per particle numerically. And then once you have this numerical expression, you can fit them to some analytical functions of the density and the gradient of the density that fulfill some exact constraints. Okay, and so this is what the Perdue-Wang 91 functional is. So there is no fitted parameters to empirical data, or I mean to experimental data, but just a fit of numerical results. Now, it turns out that the expressions of this PW91 functional for the exchange and correlation are quite complicated. So some years later, Perdue and coworkers decided to simplify the functional, and that gave the Perdue, Burke, Enzenhoff, the PBE exchange correlation functional, which is very well known. So it was proposed in 1996. So this is a simplification of PW91, where now the function for the exchange and correlation energy densities are much simpler, function of rho and the gradient of rho. And they choose to enforce less exact conditions, but still there is no fitted parameters. And to give you an idea about the conditions that they imposed, let's start for epsilon c. So they imposed basically 3 conditions. So I will define the reduced density gradient as S, So gradient of rho over rho 3, 4 to the 3 to the third. And so they impose the three following conditions. They impose that the correlation energy density um, yes, so in the limit where the gradient goes to 0, it must be equal to the LDA correlation energy density per particle plus the coefficient of the gradient expansion approximation times the reduced density gradient. Okay. But except that we don't know exactly these coefficients, but we know it in the high density limit. So they took that as the high density limit, that is when the density goes to infinity. Okay, the second condition that they imposed was to say, okay, in the opposite limit, when the reduced density gradient becomes infinity, which happened in the exponential, well, in the tail of the density, so far from the atoms, it must go to 0 because the exchange dominates in this region. And the last condition to correct the LDA is to say that in the limit where, well, the high density limit, that is when Rs goes to 0 or rho goes to infinity, the correlation energy must not diverge as it does in LDA, but it must go to a constant. And so they impose that. Now, for the exchange, they impose also the second order gradient expansion, that is epsilon x when the gradient goes to 0 must go to epsilon x LDA plus Cx, the coefficient, well, Cx2, let's say, S squared. But instead of using the exact Cx, they choose to have instead minus the coefficients that they took for correlation. And that is because in real systems, in many situations, you can find that the gradient, the second order gradient expansion cancel between exchange and correlation. And the last condition that they imposed is the so-called Lieb-Oxford lower bound, which is that the exchange energy must not be too negative. It must always be greater than some constant called the Lieb-Oxford constant times the integration of rho of r to the power 4 over 3. Okay, and we know this constant, or at least we have estimate. And so this was imposed locally, that we cannot go below that. Okay, and you can find again the actual expression of this functional in the review article. And that's yeah, okay, that's it for the GEAs. Now the last family, or the last type of approximations in the semilocal density approximations are the Metadga functionals. Do you have any questions on the GGAs? No, we can continue with the Metadgas. So the Metadgas, yeah, I should say that the GGAs are an improvement over LDA, of course. The Metadgas GGAs improve over the GGAs by introducing a new quantity. So now you have functional, an exchange correlation functional, which depend on rho and on the kinetic energy density tau. There is a question. Is it common to build exchange and correlation functionals independently? If yes, is there a general strategy to combine them, or are people just checking that some known properties are verified? Well, I will say that yes, it is. No, it is more common to build exchange and correlation functionals together. This is because very often you have some compensation of errors between exchange and correlation. So I will say that at the beginning of DFT, maybe people used to build separately exchange and correlation functionals, but after some time, most of the time they build it well, I mean, not independently. Okay, second question, is the Lie-Boxford bound satisfied for the exact R3 exchange in the place of the DFT exchange? That's a good question. Yes, I think it is. Yeah, I think it is satisfied, but maybe the form is slightly different. We have to check the chat, because you see with the R3-Fock exchange, your orbitals are different than the Concham exchange, okay? But the Lie-Boxford bound is actually more general than DFT. It was not really formulated in a DFT framework. So it works, yes, it works in fact also for R3-Fock. Yeah. Okay. So the meta GGA, as I said, are functional of rho and tau as follow. So you have some function that I will call EXC, meta GGA, can be any function. Depending on rho of R, the gradient of rho of R, possibly the Laplacian of rho of R, and this new quantity that is called tau of R. Okay, and what is this tau of R? Well, this is 1/2 sum over the occupied orbital in a Slater determinant, gradient of phi of R squared. Okay, so that's basically the non-interacting kinetic energy density. That means that it is associated to a single determinant wave function. Okay, because it is a non-interacting quantity. Okay, so that's why sometimes we write also tau of phi, where this phi is this single determinant. And this small phi here are the orbitals, occupied orbitals inside this determinant. So these meta GGAs are still considered as belonging to the semi-local approximations, because in the sense that this tau contains semi-local informations with respect to the orbitals at R. Okay. I should say that this tau of R in practice contains similar information to the Laplacian. So in practice, in modern Metadga approximations, very often, in fact, we remove the dependence on the Laplacian. We simply have the dependence on rho, gradient of rho, and on tau. So now you may ask, why do we introduce this new quantity tau? Well, there are different motivations for introducing this tau. One very important motivation is that tau is an indicator, or can be used in indicators to identify different types of spatial regions of electronic systems. And you do that by comparing the tau of your real system by the so-called von Weizsäcker kinetic energy density, which is tau W of R. And this is the gradient of the density squared divided by 8 times rho of R. Okay, the von Weizsäcker kinetic energy expression. And it turns out that if you consider one electron densities or two electron densities in a single spin orbital, in a single spatial orbital, that is, if you prefer the region of space or systems that contains only one occupied orbital, so one orbital regions, then you can show that the exact non-interacting kinetic energy is exactly equal to this tau von Weizsäcker. Okay. So then you can design indicators to identify these one orbital regions. For example, what has been proposed is an indicator that is called Z of R, which is simply the ratio between tau of W divided by tau of R. And whenever this indicator is 1, it means that you are in this one electron regions. And what you can do with this information is, for example, you can use it to try to remove the self-interaction error in the correlation functional. Okay. Another indicator that is used is called alpha of R, and it is the difference between the tau of R of your real system and tau W divided by the non-interacting kinetic energy density of the uniform electron gas, which has a simple expression. And in this case, the one orbital region are identified by alpha equals 0. Okay, so these meta-GGAs, okay, and now I need to tell you exactly how we do the calculation in practice, because as you notice, now we are out of the Conjunct scheme. Okay, it's no longer a single functional of the density. So the way the calculation is done is usually in the context of the generalized Conjunct scheme. Okay, so it means that you remember that in the generalized Conjunct scheme, we have a generalized exchange correlation functional depending directly of the Slater determinants. Well, here it corresponds to choosing for this functional the meta-GGA expression evaluated at the density of the single determinant phi and the kinetic energy density of this determinant phi. Okay, so this is a functional of phi, and this is put in the generalized Conjunct scheme. So you minimize with respect to this determinant, this expression. And it will give rise to a non-multiplicative potential. but that's not really an issue in practice. So these meta-Gga functionals are an improvement over the GGAs. And there are several which has been proposed, so I will not detail them, but just give you some name for the most famous one. So some examples. You can find again all the expressions in the review paper. There is the TPSS by Perdue and co-workers, which has been proposed in 2003. And it uses in particular this indicator Z of R. There is the M06L, which is for Minnesota, which is part of a family of functional developed in the group of J.Toulouse. And then there is also a recent one called SCAN, which is also proposed by Perdue and co-workers in 2015, and it uses this indicator alpha of R. Okay. So now we go into another family of approximation, the hybrid approximations. So 3 single determinant hybrid approximations. And first, the usual hybrid approximations. So that was in 1993, where Gga proposed to mix a fraction of Hartree-Fock exchange in DFT with some Gga functionals. And so he proposed what I will call here a 3-parameter hybrid expression, which can be considered as an approximation within the generalized Conjunct scheme. So it's a functional of phi. And it is as follows. So there is a fraction A of the Hartree-Fock exchange energy, which is a functional of phi. Then there is a fraction B of the Gga exchange, which is a functional of the density of phi. Then there is the complementary part of the LDA. Okay, decided to mix the LDA and GGAs of rho phi. And then there is plus 1 minus C times the correlation LDA functional. Okay, so it contains 3 empirical parameters, A, B, C, that were fitted to empirical data. And the exchange Hartree-Fock functional is simply phi expectation value of WEE minus the Hartree energy. And this can be written also explicitly in terms of orbitals. So you can also say that this is functional depending on the orbitals, on the occupied orbitals inside this determinant. Okay, so this the most famous such approximation is the so-called B3-lip functional. So 3 means the 3 empirical parameter, and B means that you use the Gga functional here, and lip the excuse me, I think I've forgotten one term here. I forgot the C, the GGA part of the correlation expression. Let me check. Yes, so here that was, I've forgotten C, EC, GGA. So leap is used for this Gga correlation part. And in this B3 leap, well, it was at some point the most used density functional approximations. In 1996, Gga proposed to simplify this expression, in which I will call the one parameter hybrid approximation. Again, it's within the generalized Conjunct scheme, where you have a fraction of Hartree-Fock exchange. But then you don't do this combination of LDA and GGAs. You simply have the complementary fraction for the GGA exchange. And then you have simply a GGA correlation functional. Okay. And now, of course, it was proposed for the GGA, but in practice here you can use a meta GGAs. Okay, it works as well. So now, what should we take for this fraction of Hartree-Fock exchange? Well, in practice, it turns out that an optimal value is often around 0.2 or 0.25. Okay, so why introducing a fraction of Hartree-Fock exchange? That's because you are going to reduce, for example, the self-interaction error. Okay, so now you may ask, okay, but why not having completely the entire Hartree-Fock exchange, nothing for DFT for exchange and only DFT for the correlation part? The problem with doing that is that then you don't have this compensation of errors that you often have between DFT exchange and DFT correlation. So in practice, the fraction of Hartree-Fock exchange, because of this compensation of errors, should not be too large. And so that's why the optimal value is often around, let's say, 0.25. So this has to be used in the generalized Conjunct scheme. And if you calculate the potential associated to that, because of the Hartree-Fock exchange, you are going to find a non-local potential, but that's okay. That's manageable within this generalized Conjunct scheme. Now, let me give you some examples of hybrid functionals. So there are different philosophies here as before. So for example, you have the PB0 functional, where you take the PBE functional for both exchange and correlation. And you take as a fraction of Hartree-Fock exchange 0.25. And this is, in this case, not fitted parameters. It is fixed to this value without trying to optimize it. And for this reason, it is called PB0 because it means there is zero fitted parameters. Another example of a hybrid functional is the TPSSH, where H is for hybrid. And in this case, with the Metadga functional, typically you need a smaller fraction of Hartree-Fock exchange. So here they have optimized the parameters and they found A equals 0.1. Okay. So that's, I would say, examples of hybrid functionals with minimal empiricism, with not many parameters. But now you have another type of hybrid functionals, like the Gga 97 functional, where you have some sort of systematic polynomial expansions in terms of some variables, and you systematically optimize all the coefficients with respect to experimental data. And for example, in this functional, you have 13 parameters. And another one is the Minnesota 06 functional, where it contains 36 parameters. Okay. Now, another type of hybrids are the so-called range-separated hybrids. And so that was based on an idea first proposed by Savin in 1996. But then it was applied in this form by Hirao and co-workers in 2001. And it was called the Long Range Correction Scheme, LC. And the idea is to take an exchange correlation for this long-range correction scheme as follow. So this is within the generalized Conjunct scheme. You have the fraction of Hartree-Fock exchange, but now you take only the long-range part of the Hartree-Fock exchange. Okay, so what does it mean? It means that in the expression for the exchange energy, you replace the Coulombic interaction between two electrons, 1 over R, by a long-range interaction. In practice, we often take this interaction made of this error function, F, of mu R over R. So if you plot this interaction, you will see that this is only the long-range part of the Coulomb interaction. And this parameter mu gives you the range of the interaction. So in practice, it is a parameter. It is often around 0.3, 0.5. And this is inverse Bohr. Well, okay, so that's the long-range Hartree-Fock part. And then you have the complementary short-range GGA, or meta GGA if you prefer, depending on the density of phi. And then you have the correlation functional. So why do we do that? Well, again, it allows you to reduce some error in the exchange by introducing Hartree-Fock exchange. In particular, the property depending on the long-range Hartree-Fock exchange are better with this approximation. And also it makes easier to find good approximation for the short-range exchange functional, because the type of approximation like LDA or GGAs are better if they are restricted to the short-range part of the interaction. So of course we have to define new approximation here, but this has been done. And for example, one popular approximation in this family is called LC omega PB. Omega is another name for this range separation parameter mu. Okay. Now, in 2004, Handy and co-workers proposed to a slightly different decomposition. They call it CAM for the Coulomb attenuating method, where they have the following decomposition. They have a fraction A of short-range Hartree-Fock, and then a fraction B of long-range Hartree-Fock. And then they have the complementary DFT part, so 1 minus A for the complementary short-range GGA exchange. And then the complementary, so 1 minus B long-range GGA. And then correlation part. Okay. So you see it contains, as a special case, the LC scheme, where you take B equals 1 and A equals 0. But it's more general than that. So now you can introduce, if you want, a fraction of Hartree-Fock exchange at short range. And this gives you more flexibility. And you can, for example, remove more of the self-interaction error at short range. Okay. But of course, you have more empirical parameter. And so the specific approximation that proposed in this scheme is called CAM B3-lib, based on the Becquet and the Lib functional, which is a quite used functional, in particular for charge transfer excitations. Another example of functional in this family is the so-called omega B97X, okay, which is based on the B97 hybrid functional, but it doesn't use the full flexibility because it uses B equal 1, so it imposes really the long-range Hartree-Fock exchange entirely at long range. There is one question: why 0.25 as contribution for the Hartree-Fock exchange in the PB functional, for instance? Is it a good empirical value? Well, okay, so let's say that in practice, it was found empirically that a value around 0.25 is good. But then there is a paper by Perdue and co-workers who find a rationale for this value based on an argument based on perturbation theory. So because of this paper, it is considered by some person that this value is non-empirical, but it is a theoretical value, okay? But it is arguable. Some other people think that it is still an empirical value, okay? So there is a debate about that, but anyway, it is a good value in practice. Okay, so let's continue. We are almost done. Yeah, so the last thing that I want to talk about is, as I promised at the beginning, multi-determinant hybrid approximations. Okay, and first, the so-called double hybrid approximations. Okay, so this family of approximation was proposed by Grimme in 2006, and the idea is, so I will call them two-parameter double hybrids, like this. And the idea is to have a fraction Ex of Hartree-Fock exchange, okay, with the corresponding complementary fraction of exchange Gga. That's like the hybrid. But then you have a fraction of correlation in Gga. And then you have a fraction of MP2 correlation. Okay, so that's the MP2 correlation energy. So it's a double hybrid in the sense that not only you have a hybrid between Hartree-Fock and DFT for exchange, but now you have a hybrid for correlation between MP2 and DFT. But of course, MP2 cannot be done in a variational way. So what you can do is that you calculate this in the self-consistent field in a self-consistent way, and then you add a posteriori the MP2 term, okay, at the end of the calculation. An example of such functional, the first one that has been proposed, is called B2PLIP, and it uses the Gga functional for exchange and the LIP functional for correlation. And the parameters has been optimized, so it was found a fraction of Hartree-Fock exchange 0.53 and a fraction of MP2 correlation 0.27. And so you see what happens is that because the use of non-local correlation, you rely much less on compensation of errors between exchange and correlation, and therefore you can have a much larger fraction of Hartree-Fock exchange. Okay, you double basically the fraction of Hartree-Fock exchange, and for this reason you reduce the self-interaction error. So you improve the thermodynamic properties for a lot of systems, except for system with strong correlation, because in this case, MP2 doesn't work, okay? But if you have a system with, let's say, a large HOMO-LUMO gap, then it tends to improve. Now, this sorry, I have a question here in the chat. This range separated parameter mu might depend on atom size. Yes, so that's a good question. So here, the normal way to do is to have a fixed value of mu for all the systems. But in practice, something that is much flexible will be a mu that adapts to each system, and it has been proposed. Or even better, will be to have a mu that is a function of the density, for example, which depends on R. But the problem with that is that it's more complicated to implement, but there is an interest in developing such approximations. Now the question is, the parameters are optimized with respect to empirical results or more accurate method like CCSD, parenthesis-T, or else? Well, it depends. In some cases, it can be empirical results, I mean experimental data, or sometimes it can be methods like CCSDT. I think most of the time it's experimental data, but okay. So the double hybrids, in order to understand them, it was proposed in 2011 by Sharkas, Savin, and myself to view them as an approximation of a multi-determinant Conjunct scheme. And so, in fact, I will not explain that in details, but basically you can find this extension where you minimize now with respect to a multi-determinant wave function the expectation value of t plus VNE, but now you add a fraction of the Coulombic interaction, a fraction lambda, and you have a complementary functional for the rest of the interaction that I call E bar of lambda, depending on rho of psi. So this is exact in principle as in Concham, okay? But now you have a multi-determinant wave function. And if you use perturbation theory at second order within this expression, you can find what we have called a one parameter double hybrid approximation, which has the following expression. You have the fraction of Hartree-Fock exchange, which is given by this lambda. Okay. 1 minus lambda times the, let's say, GGA, if we use such an approximation for the exchange. And then you will have 1 minus lambda squared times the correlation GGA. And then you have lambda squared times exactly the MP2 form of the correlation energy. Okay, so it's a sort of justification of the double hybrids using this scheme. And also it tells you that you don't really need two parameters, but in fact the fraction of MP2 must be simply the squared of the fraction of R3 fog, which is approximately what you find here empirically. Okay. Okay. And in fact, Emmanuel Fromager has an extension of this in order to allow for two parameters. You can also go beyond the second order perturbation theory within this scheme. You can also use an MCSCF a wave function to have different types of wave function DFT hybrid schemes. And now the last family of approximation are what I will call the range separated double hybrids. Okay, and so that was really, I mean, a multi-determinant extension of the Conjunct scheme that was proposed by Andreas Savin in 1996 in the present form. And it is as follows. So you obtain the exact ground state energy by minimizing with respect to a multi-determinant wave function the expectation value of t plus VNE. And here we have only the long range part of the Coulombic interaction, again, which is realized in practice with this error function. And then you have a complement functional that I will call E bar short range for the remaining short range effects. Okay, so again, this is an exact decomposition. It's similar to what we did here for the lambda, but here it's with the range separation. And you can use this scheme with any type of wave function that you want. You can do an MCSCF, okay? You have an MCSCF plus DFT scheme. But in order to have some sort of double hybrids, what you can do is again develop a second order perturbation theory starting from this exact expression, and it was done with Angian, Gerbert, Savin, and myself in 2005, and we obtain a sort of double hybrid approximation, but with range separation. So essentially, this is a method that we called range separated hybrid plus MP2. And you will find the long range R3 exchange. Then you will have the complementary short range, let's say GGA exchange. Then you have the complementary short range GGA correlation. And then you have the long range MP2 correlation, okay? And the advantage of this scheme is that, well, first, you only need the short range component of the exchange and correlation DFT functional, which are easier to approximate with a semi-local approximation. And now you have an explicit MP2 term for the long range correlation part, and this can be used to compute dispersion interactions, okay, which are part of the van der Waals interactions. And also the fact that MP2 is only for the long range means that you will have in practice a fast basis convergence. Okay, but because that's the short range in MP2 that leads to a slow convergence. So you sort of combine the advantages of the two worlds. you can also combine the idea of this range separation and this lambda separation, okay? But I will skip that. And let me just finish. Okay, there is a question. Will the results for the exchange correlation in the multi-determinant Conjunct scheme formula that you proposed be reasonable if the energy is minimized with respect to a single determinant? Well, in this case, it is an approximation. So basically, that's a good question. So if you take, for example, this expression, and now you make the approximation that you use simply a single determinant phi, what you are going to obtain is basically an expression like that without without the MP2 term. And so it is similar to a single hybrid approximation. Okay, so it is reasonable, but we can go beyond that. It is in fact a way of understanding the hybrid approximation. I will say this is one approximation of this exact scheme. Now the question, is it possible to use other electron correlation methods other than MP2 for the double hybrids, or it's too computation demanding? Yeah, that's a good question. Yes, we can absolutely do that. So we can, instead of having MP2, we can go to higher order of correlation. We can use, for example, what is called the random phase approximation, which has been developed a lot. Okay. You can use also Kappa cluster. Yeah. Okay. And this is perturbation type theories, but you can also, as I said, use non-perturbative expression for the wave function. You can use MCSCF, you can use DMRG, whatever, to combine DFT and wave function theory. Okay. Okay, so maybe the very last point that I want to briefly address, because it's important in practice in actual approximation used. So 5 are the semi-empirical dispersion corrections. Where, you know, if you use this approximation here, the van der Waals will be sort of included in the MP2. But in all the other approximations that I showed you, the dispersion interactions are missing, or at least partly missing. So people have developed a semi-empirical expression to include, to add to your functional an expression for the dispersion interaction. So it usually looks like that. You have an empirical constant to adjust to any functional, and then you sum over the pairs of atoms in your system, alpha, beta. Then you have what is called a damping function, depending on the distance between atom A, atom alpha and atom beta. Then you have London dispersion coefficient, C6, for the atom pairs alpha beta of your system, and then you divide by the distance between the atoms to the power 6. So that's the dispersion interactions. The C6 comes from tabulated data, or sometimes they can be calculated in different ways. And this scheme is often known as DFT D. D for dispersion. So sometimes you find some functional and then you add the D, and it means that you add this term. And it is quite fast. It works quite well. But there is also another way of including the dispersion interactions, which is the so-called non-local functional. Okay, which is basically you add to your functional a non-local functional of the density of the following form. So let's say 1/2, then you have the density at rho 1 at R1 and R2, and then you have a kernel, let's call it phi, of R1 and R2. Okay, so that has a complicated expression in terms of the density, and you need to find an expression in order to reproduce the dispersion interactions. And there are two main functionals in this family, the so-called VDWDF, and also the Vidroff-Van Voris VV functionals. Okay, so it's a little bit more complicated than the semi-empirical dispersion corrections, but in some sense it is more robust because it is less fitted. Okay, so that's basically the end. I see that there is one question. To compute the MP2 energy here, we use the normal equation of MP2 based on R3-Fock orbitals, or there are another equations for MP2 energy using constant orbitals. Yes, so we don't use the R3-Fock orbitals. So if I take here the expression, so we first do this calculation self-consistently. So it won't be the R3-Fock orbitals that you are going to find. It won't be also the Conjunct orbitals, because that's another scheme. Okay, so that will be the orbitals corresponding to this energy expression. And then you use in the normal MP2 expression these orbitals and orbital energies. Okay. Okay, so that was a panorama of approximations. Maybe I should mention that there is also the family of orbital-dependent functional in the so-called optimized effective potential scheme, like the exact exchange or the Gerling-Levy perturbation theory, or even the random phase approximation is sometimes considered as this. But there are more complicated expressions you can read in the review papers, and I will say they are less used so far than what I've talked about. Do you have any questions? Yes, so you mentioned the compensation of errors between the exchange and correlation part of the exchange correlation functional. What is the nature of these errors? Well, okay, this is a bit complicated, but I will say, okay, I mentioned a lot the self-interaction error in the functional, for which tends to give you too low an energy. It tends to delocalize too much the density. But there is another error which is more complicated to see, so I didn't talk really about it, is the so-called strong correlation error, which comes from the fact that when you have systems with small homolumo gaps, you have strong correlation, and you have also an error in the LDA or GGA approximations. And this error has sometimes the opposite sign, because it tends to give you too high an energy. And so in practice, you often have in LDA or in GGA a compensation between these two types of errors. Okay. And that's why, for example, if you use a hybrid approximation, so with some fraction of R3-Fock exchange, you tend to reduce the self-interaction error, but you also tend to increase the strong interaction error. And so that's why sometimes it is advised, when you have a strongly correlated system, to use zero fraction of R3-Fock exchange. So there is always this difficulties about these two types of errors in DFT. Other questions? Okay, so if not, I think we can stop here. Thank you for listening.
Thank you very much, Julien.
Thanks
Thanks a
you.
lot.
Okay, so have a good day and see you next week for the next course. That will be
Yes,
Pierre-François, right?
I think so, yeah.
Mm.
Yes. Okay. Thanks again. It was very nice. Thank you.
Thank you. Bye-bye.
Bye bye.
Bye.